welcome. I'd like to introduce theoretical computer science, and one of the main questions of theoretical computer science is that of efficient computability. We discovered a lot of problems that we can compute efficiently, and we denote this class of problems as P. And in theoretical computer science, we also discovered that a bunch of problems we were not capable of solving efficiently, and we discovered a mathematically rigorous underlying reason, which we call NP completeness. And the intuition is that there's a combinatorial explosion of possibilities, which explains why we cannot solve those efficiently. TCS, theoretical computer science, has two main contributions to this NP completeness. First of all, we showed general awareness to all of science. Second of all, we developed a huge bunch of possible techniques that can be used and can be applied to NP-complete problems. There's a level of difficulty in the last decade that's been named ER completeness, which is conjectured to be even more difficult than NP-complete. Intuitively due to two reasons. One is that the solution space is continuous, but also nonlinear. This proposal, I want to work on ER completeness, and I want to create awareness for it, and I want to develop techniques to deal with those problems. In the next slides, I would like to show you 3 example problems so that you get a feel for those problems, and also I want to focus on those problems in this proposal. First problem is the so-called art gallery problem. So art gallery problems here an analogy, and that's an old problem in computational geometry that is very widely studied. Here we've given a simple polygon presenting an art gallery, and we want to protect all the art, placing guards, which we model as points. The aim is to place as few guards as possible to protect the entire gallery, in this case 4. You can see that a guard can be placed anywhere inside the polygon, so this makes this problem continuous. And the nonlinear movement, or the nonlinear change of the visibility region, makes the solution space nonlinear. Second problem I'd like to introduce to you is that of geometric packing. Here we've given a container and some items, and we want to place all the items inside the container. To illustrate how difficult our complete problems are, note that we do not know if this is the smallest square container to pack 11 unit squares. So already for 11 unit squares, we cannot solve this packing instance. Again, this is problem is continuous and nonlinear. Continuity is clear because we can move pieces continuously. And to see nonlinearity, if you rotate one of the pieces, then another piece gets pushed aside in a nonlinear fashion. Third problem I'd like to introduce is that of training neural networks. We've given some data, some network architecture. We'd like to fit all the data by the network. Here, this is a continuous nonlinear optimization problem. This is a little bit more difficult to see because it's too involved to give you the definition. But yeah, again, this is one of these difficult problems. In my previous research, I showed that all of these problems are actually equally difficult. Namely, all of them are ER complete. So that makes this intuition a mathematical rigorous statement. And there are also a host of other ER complete problems that I'm not going to talk about. So now that we know that there are fundamental important problems ER complete, the next step is to develop some algorithmic theory. ER completeness tells us that this is in general not possible, but it is with additional assumptions. I set myself the 3 goals of having guaranteed optimal solutions, provable time bounds, and efficiency in practice. That's the whole grail, and that's what I want to achieve within this proposal. Let me go through existing algorithmic techniques and what they're capable of doing. Symbolic methods are maybe the oldest methods. Here, to give an illustration, this polynomial has odd degrees, so we know it has a 0. So we can decide, yes, this polynomial has a 0, without actually knowing how the polynomial looks like geometrically. These types of methods stem from real algebraic geometry, a great in theory, horrible in practice. Second type of methods, gradient descent or gradient-based method. Here we've formulate our problem as a finding the minimum of a continuous function, and we can compute the gradient. It's very efficient in practice, but comes without theoretical guarantees. Both methods are widely applicable to all types of ER-complete problems I wanted to mention. A third type of method is discretization. Discretization, instead of considering all points where we can place a guard here for this example, we just restrict ourselves to a finite set. And this finite set could be a grid, or it could be defined in some other more convoluted way, or could also be adaptive. And so discretization schemes have the potential to satisfy all the three goals. And the novel part is to devise specific discretization schemes that actually satisfy all the three goals, that achieve all of them. So discretization schemes have been used before. So what's the scope? Again, I'd like to study all ER-complete problems, having a focus on the first two in the first work package, because of their geometric, tangible nature, they should be somewhat easier to tackle. A second work package, I'd like to focus on trained neural networks because of its potential large impact. A third work package will try to generalize the lessons learned from the first two. As the reviewers highlighted, this is a challenging project, but they also showed confidence in me achieving this, and this confidence stems from previous research which showed feasibility. So for the ArtGrid problem, I showed this is possible, and I would like to illustrate how. So we formulated discretization schemes here. We proved optimality using replacement arguments. We bounded the size of the discretization schemes. We implemented and tested it. Here you can see the optimal solution for some benchmark instances. And all of this was possible due to new types of assumption, which I call solution stability. And you also can read something in the proposal about ILP oracles. With these new assumptions, we reached all three goals and showed them in the paper. So there's hope that now these types of methods and these types of assumptions can be generalized to other ER-complete problems as well. Also for the ArtGrid problem, there remain challenges. We'd like to show better time bounds and be actually faster in practice. What will be the impact of this proposal? First, there will be a deeper understanding. Specifically, this means a stronger awareness of this general phenomenon of ER-completeness, but also developing techniques to tackle those ER-complete problems. Second, this could have long-term applications. These techniques can be adapted, for instance, by the machine learning community, and we may be capable of training smaller neural networks which are more energy efficient, and these theoretical guarantees, they could be useful, for instance, for ethical reasons, right? That we want to say, okay, these neural networks are gender neutral. How do I want to do this? Well, I already have a record of publishing outside of theoretical computer science, and I will continue to also do this. Of course, I also publish within TCS. Furthermore, I have a YouTube channel with which I make my research more broadly accessible to a wider community of researchers. Why am I the right person to perform this type of research? First, I have a strong record on working on ER-complete problems, and as the reviewers pointed out, I'm one of the movers of the field. One of the signs of this is that I have key publications at JCM, SciComm, FOG, Europe's, showing, for instance, that these three problems are ER-complete. Second of all, I'm by the reviewers described as a leader. Maybe I would rather say I really enjoy working together with young researchers. I think I have a philosophy to motivate young researchers, PhD students, master students, or also postdocs. And as you can see, they also seem to really enjoy working with me. And with this, I'd like to thank you for your attention.